A gram-scale probe equipped with a photon sail catches a concentrated laser array and accelerates to 20. We are aiming an unguided projectile at a specific planetary coordinate 4.25 light-years away. If the trajectory occurred in a true vacuum, hitting the target would be a trivial exercise in constant velocity special relativity. But space is not empty. The probe's flight path is anchored by a massive perturbing body immediately upon launch, our own Sun. Moving through the Sun's deep gravitational well at a fifth of the speed of light induces relativistic perturbative effects that leading-order Newtonian constants simply cannot resolve. Hitting a precise coordinate across interstellar space requires mapping the subtle gravitational topography worked by our host star. To calculate the exact deviation, scientists ran the flight path through Pomni, an n-body gravitational dynamics solver, strictly using a Newtonian gravity model. Warning tone. They found that ignoring relativistic effects creates a trajectory error resulting in a misdistance of nearly 690,000 kilometers. Correcting Ristreft requires the post-Minkowskian, or PM approximation. This mathematical model calculates general relativity over a flat Minkowski spacetime, breaking the physics gown into a three-part Hamiltonian. The first term, h1, isolates the special relativistic kinetic energy of the probe. The second term, h2, maps the standard Newtonian gravitational potential of the solar system bodies. The critical third term, h3, accounts for the first-order general relativistic momentum corrections acting on the spacecraft. Hamilton's equations generate a system of highly complex, nonlinear ordinary differential equations. To solve them, researchers employ dual-number automatic differentiation, turning numerical targeting into a machine precision route-finding problem. When executed correctly, this algorithm fine-tunes the initial launch velocity to achieve femtometer-level targeting precision across the entire 4.25 light-year span. Relativistic gravitational corrections are the absolute mathematical baseline needed to ensure the probe reaches the target system. Upon arrival, the physical challenge shifts. Proxima Centauri is an active M5.5 dwarf that operates on a violent 7-year magnetic cycle. The space weather modeling framework maps this system. The top sphere isolates the surface magnetic field. This couples to the stellar corona, where purple lobes represent the Alpha surface intersecting inner orbits. Finally, it maps the inner heliosphere, capturing the current sheet and outer trajectories. This visual highlights the orbital architecture of the inner candidate planet, Proxima d, positioned just 0.029 astronomical units from the star. At this proximity, the planet physically crosses into severe sub-Alphenic stellar wind sectors during the star's maximum activity phases. The stellar wind dynamic pressure here scales to thousands of times what we experience on present-day Earth. Violent streams of plasma aggressively impact the planet's surface, relentlessly shearing away any fragile atmospheric gases into open space. The simulation proves that mere proximity to an active M-dwarf subjects a planetary body to catastrophic atmospheric stripping during magnetic peaks. Moving further out into the heliosphere, at a distance of 1.44 astronomical units, we reach Proxima c. This Mercator projection maps the dynamic pressure distribution for this outer orbit. During an activity maximum, the intense pressure is largely contained within a specific equatorial band. This chart illustrates the orbital phase variation. By tracing the data along the planet's inclination, we find surprisingly stable Earth-like stellar wind pressures along Proxima C's specific path. This 3D model reveals how the localized magnetosphere shields the planet from incoming plasma under maximum stellar activity. The density-colored streamlines deflect cleanly around the bow shock, compressing the dayside boundary, but the bulk of the plasma bypasses the planet entirely. To measure the residual energy dissipation, physicists calculate the resulting Joule heating absorbed in the upper atmosphere. Assuming a standard 0.3 Gauss planetary dipole field, the Joule heating reaches only 10% of Earth's nominal value, a result of the weak interplanetary magnetic field at this distance. Measured, resolving tone. Despite the host star's violent activity maximum, sheer spatial distance yields a local plasma environment for Proxima c that is remarkably comparable to our own solar system. By combining these two frameworks, we establish a complete interstellar mission architecture. Precise target acquisition relies heavily on calculating the exact astrodynamics of general relativity. Destination survivability is dictated entirely by a planet's spatial relationship to its star's Alpha surface. Layering post-Minkowskian gravity models with multi-domain magnetohydrodynamics bridges the gap between abstract physics and actual mission execution. We have moved the Proxima Centauri system out of theoretical speculation, translating it into hard, actionable engineering data for an interstellar launch.